was, let me go back. What was in push and pop? What was a push? Yeah, it was a stack way of saying adding an element. Pop is stack way of saying removing an element or deleting an element. What was the stupid example that I give you? If I wanted to find out how many elements in the stack, can I use a pop? Can I use a pop? Yes, but is it a good idea to use a pop? Because? If I start using the pop, I will be removing the elements from the stack. So after I got the total length of the array, total length of the stack, nothing will be left in the stack. So I will be getting something old value of it and stuff like that. I mean, I'm using some of the functions inside of other functions. Those are the key ideas. That's why we take a look at the array implementation of linear list implementation of using arrays to represent some of the functions in here. That's why we start looking at like inheritance. Some of the functions we can just directly use it inside of this stack implementation. As you can see, you can just use the previous ADT of the array list they call it, as it is. What else? Return bool empty. Just simply I'm using the empty function, empty operation from array list. It was previously defined before. 그죠? Likewise for the size, I'm using the same function that has been implemented for array list. For top, what is it? Top again? Top and bottom. Where am I adding an element to? Which point? In stack, where am I adding an element to? 얘기하기 싫어? 얘기하기 싫어? 아이고, 뚜껑 닫고 먹으려고 그래. 정신 나갔구나. You're adding an element to a top position, right? Am I wrong? Usually the things at the bottom will be the last one, will be out of the stack, 그죠? 오, 전혀 집중을 못하는 이 너무 쉬워서 그런가 보다. 뛰어넘지 뭐. Okay. Pop, push. I know you guys all know this. And they was saying that some of the programs that you can take a look at it, but we already seen a stack implementation using array stack. No, using array. 뭐야, 이름이 it's all the same. Array list. It's not a good naming in your textbook. Sometimes I got a bit confused. And they were saying sometimes it may not be very efficient implementation here. Even for the linked list way of implementing stack. What was the one example to show you that which one is efficient, which one is not efficient? In terms of order, big O or theta here, theta 1 and theta n. What was the problem with those linked list way of implementing this stack? Or you're not just getting me today. Am I speaking too fast? 아니잖아. 그죠? Or should I stop asking questions? 이 한 주에 오늘 내일만 하면 다시 휴일이 돌아오는데 이렇게 이 기쁜 한 주를 앞두고 이렇게 주 4일만 했으면 좋겠지. 프랑스 애들은 주 4일 하더라. 너무 노니까 할 일이 없어서 휴일에 회사를 가게 되는 악순환이 펼쳐지긴 하는데. 정신 차리고. What am I? Linear list using a linked list to implementing stack. And it was talking about some efficiency issues there. What was the problem? What was the main issue? Linked list. 뭐야? Those of you who came in late, this is our midterm schedules. Don't send me emails again. Now, I already got 10 emails asking about the midterms. I don't understand why. We still have 2 weeks, 3 weeks to go. 내가 이메일이 귀찮아서 그러는 게 아니고 이메일 함을 도저히 청소를 할 수가 없어. 너무 많아가지고. 서로한테 한번 물어봐. 알았죠? Link list. Problem comes, which end is top, which end is bottom, 그죠? If I put this end as a perhaps top, I need to add an element to the top based on the definition of stack, bottom. So in order to add an element, I have to go 1, 2, 3. 아니다, 1, 2, 3, 4. So at least as much as number of elements, I have to go there at the end, adding an elements in here. 그죠? Something like this. It might be much easier just do it in top and bottom. Just changing around the pointer is a constant operation, usually say as order 1. Constant operation is much less. Then you have to go through the loop again to go to the location to find it. So that was a brief review on using a linked list way and a faster implementation, as well as array example. We'll also take a look. Okay. In terms of array, what was the one way to use, implementing two arrays, two stacks? I'm sorry, I keep mixing up the word array and stack. Implementing two stacks into a single array. What was the one way of doing it? I also draw on that board. Also, it's on your textbook as well. 뭐였어? I'm not asking you to code. I'm just asking you to draw a figure like this. 이번 주에 그냥 휴강 할 걸. 얼마나 좋아 그럼. 이번 주에 수업 하나도 없는데. Huh? Yeah, top, maybe I have two tops. Top 1, top 2, bottom 2, bottom 1. You grow this way. How can you make sure these two are not met or mixed up? When you actually do the code, hopefully you can add some safety mechanism, like asking questions whether you're seeing another elements at the end or something like that. It might be another way of doing it, right? This is a general idea. Why are we doing this for? What was the main reason of suggesting something like this when you're implementing a stack? 뭐라고? 다시 해봐. Space distributions. So we don't want to waste the memory. I mean, if you declare an array, usually we don't know the stack. We don't know how many elements will be coming in. So it's a bit dynamic, not fixed size. But when you declare array, usually fixed size. So it tends to declare a large number of elements in the array, like array 100. So most of the time, in our example like these, you're wasting 90% of the space. So in order to save some space complexity, those are the suggested. I mean, it's also important to draw how to graph like this. Also, you have to know the basic, what was the main idea of doing this. I mean, it might be helpful to answer some of your multiple choice questions. Do we have multiple choice questions? 미치겠다. I don't think so. Yeah, I don't think so. Probably not. 모르겠다. I don't guarantee. I would take a look and let you know next week. 이게 기억이 안 나냐? 그죠? This was the one that I said one is theta n, the other one is theta 1, but I also said it's okay to say order 1 or order n in the worst case. Chain. I usually say linked list, but they usually here in the textbook as well as your slide often call it as a chain and node, okay? Do not mix it up. And then what was the another probably the first example using stack that we saw. Huh? left hand 어디서 스택에서? left hand가 탑이다 바텀이다를 정해주는 거지. left hand는 그냥 이쪽 right hand 이렇게만 하고 left hand를 탑으로 갈 건지 left hand를 bottom으로 갈 건지 그거는 또 이렇게 나오는 거예요. left hand라고 해서 탑이라고 하는 건 아니고. 아 이거 left hand잖아. left hand가 탑일 때 효율적이다.
탑이 왼쪽에 있을 때가
left hand가 탑일 때 탑이 left hand가 탑일 때 오케이? 헷갈렸다 나도 갑자기 그죠? left hand 맨 왼쪽에 있는 걸 탑으로 할 때 efficient하다 그렇게 써놓은 거예요. 그 두 개를 바꾸면 갑자기 다른 말이 다 보이지 그죠? 무조건 left hand라고 해서 탑은 아니에요. 그렇게 하는 건 아니고 그죠? right hand가 탑이게 하면 stack it's also okay to use a right hand to be a top. Just one small problem is maybe slower than when we use the left hand as a top. So that's the only stuff. 둘 중에 하나 고르래 해서 여기다 left hand 이렇게 써는 거야. right hand냐, left hand냐. What would you use? What would you use? So the other one was parenthesis matching. I went through some of the examples in the textbook. It's pretty much simple, right? As soon as, what was the algorithm that I wrote down here? It's also very similar looking pseudocode in your textbook. What was the simple pseudocode that I wrote here using stack? First, in order to solve this, how many stacks do you need? In order to maybe solve the first question. We all know what the question is. How many stacks do you need? Huh? Do I need 2 stacks? Raise your hand. How many? 1 stack. 2 stack. 3. Infinite. No one cares. 큰일 났다. 이렇게 비협조적으로 나올 거야. 2. Why do you think it was 2? 그냥 잠깐 헷갈린 거지? 그죠? I just need a 1 stack. You push into the stack. When you see a right parenthesis, what do? You pop it out. And you just record the location of each parenthesis and you put that as a pair and print it out. That's the problem they ask you to do. You can definitely write your own program with this, and this just the same way that I showed you last time. And most likely questions like I leave out the blank. And I probably give you a set of operations that you can use. I might mix it up. I might use some other ADTs from other data structures, and you have to pick one and you have to write it down. And that's the typical questions. Like it's quite easy to do once you know what this is doing. And I don't think I need to do this again. So that's the parenthesis matching problem. Like I say, these might be the basis of your syntax checking on your compilers. Compilers, if you write something wrong, you miss a semicolon, you miss a parenthesis, they usually give you error message line 10 have an error. Stack is one of the basic way of checking those syntax in it. And I don't think we have in our curriculum we don't teach you that, but I mean, a simple example like this give you idea of how to do that. How to implement this using stack, just again, scan expression left to right. When a left parenthesis encountered, when you see the left parenthesis, add its position to the stack. When the right parenthesis is encountered, remove matching position from the stack, blah, 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 just like what I said. And it was an example like this. I mean, you can just go through once, you will know what it is. Just don't leave it out. And just don't scare me with the 2 stack. I only need 1 stack of doing this. See, 8.6, it's pretty much same as what I showed you last time, the pseudocode that I wrote on the board. Do the same for this. And there was towers of Hanoi. We know what it is. Simply, what was the problem definition? I like to move everything in A to C using B. But there was a two condition, moving one disk at a time, plus you cannot put the larger one on top of the smaller one. That's the only condition. That's why you need the B to do this. So in a way, how many, if you wanted to program this, how many stacks do you need? So 3, maybe 3. Because ABC is quite obvious. Quite obvious. Last time I did this wrong and I show you how much my IQ is. So I think you guys are okay with this. Okay, finally do this. But if we counted how many moves that you have to make was, I think if you count this for 3 disks, it was 7 moves. How many moves that are needed for solving 3 disk towers of Hanoi problems? 3 disk, and it was a 7 move. This time we actually do it ourselves, so we can compute that. 7. How we get that? It's a great solution for recursion. I'm not going to go into too much details in the recursion. If you read your textbook, they want you to take a look at some of the examples in chapter 2 when they actually going through some of the recursion approaches. But basic idea is this. If you actually take a look at the program of 8.8 in your textbook, it's only 1 line or 2 lines of code. It's a one small function of doing it. Basic idea is I have this. It's not a disk. I have 3. I have a stack of this here. It's also disk. Idea of recursion is very, in a way it's simple. In order to move this to here, in order to move that, I need to do this for everyone, same step again. So I give this as a smaller problem to towers of Hanoi. I break it down into problem. After I do this, I take care of this smaller set. I call the towers of the Hanoi function one more time for smaller data sets. So inside the function, you call it again with the smaller data set. You reduce one by one. I would also try to write that in a function. So if I wrote maybe I need a function called the towers of Hanoi. Maybe I need 책이 어떻게 썼는지도 잊어버렸는데. Anyway, I have that. Maybe I just need 2. I don't care. So I give that as a data set. Maybe jet as data set may not be the same as in the textbook. It's a similar idea. X, Y, Z. So I put somewhere, one of the parameters is the data. Another parameter is data. Maybe I call this as n. I have n disk. Okay. I put n disk. This is maybe X, Y, Z. I don't know. X, Y, Z. I give input, I give 2 stacks to solve this, move the disk around. So inside of this function, I do something in here, move something in here. Inside this function, I'm going to call myself again. N minus 1 now. So imagine I'm in this function again. Imagine I'm in this function again. Then inside this function, it will be n minus 1, n minus 1. n minus 1, n minus 1, n minus 1. So you break it down into bottom of it, and when you're done the bottom function, the very last function, you move back again to solve the bigger problem. The same thing as you break it down, you look at this as one Hanoi problem, another Hanoi problem, towers of Hanoi problems. That's idea of recursion. Why is it recursion again? It's calling itself. 자꾸 들어가니까. In Korean, briefly, 아주 그냥 간단하게 생각해서 어차피 하나를 옮겨야 되는 거 아니에요? 그죠? 하나가 일단 일로 가야 그 다음 것도 가니까 하나를 옮기는데 내가 만든 Towers of Hanoi라는 이걸 푸는 펑션을 콜을 했어. 이만큼 데이터셋에 하나 옮겼어. 그러면 이만큼이 남잖아. n-1분이 남잖아. 이거를 다시 Towers of Hanoi 펑션을 또 주는 거야. 그러면 여기서 또 하나 또 남잖아. 요만큼 남은 덩어리를 다시 주고 요만큼 남은 덩어리를 다시 주고. So you can actually do this way. This is a very simple way of doing it. Problem with the recursion, like we briefly discussed at the beginning of class, not beginning of the course, it's taking a lot of time, taking a long time. They said it's exponential. If you do this, it would take a 2 to the n times minus 1. So a big O of 2 to the n. I don't know how to draw a 2 to the n graph. How do you draw this? y 2 to the x. 이거 어떻게 그려야 돼? I don't know. Maybe it's like that. Maybe at the end. I don't know. You can figure this out. Exponential. But it's much faster than n squared and n to the cubic or any of the functions that we have looked at so far. 그죠? So minimum number of moves required is 2 to the n minus 1. So example that we saw was what? 뭐지? n was 3. So 2 to the 3 minus 1 is 2, 7. Y is 2 to the n minus 1. Next slide, we'll have that. Time complexity of the Tower of Hanoi is theta of 2 to the n, which is exponential. It should be big O of 2 to the n. It's the same thing, but since disks are removed from each tower in a LIFO, last in, first out manners, each tower can be represented as a stack. Each tower represented as stack. See program 8.8 for Towers of Hanoi using stacks. It would very much look like this. Probably the order of the parameters is slightly different. I don't know which way it was. 아마 이게 순서만 좀 바뀌고 똑같을 거예요. This basic idea is calling it again with the smaller data set. Recursive solutions. This is on here. So I need to move one. Rest of the stuff, I just put it as another big problem, minus 1 disk. N is greater than 0 gold disk to be moved from A to C using B. Well, whatever I have to do, I just go through the B. Move the top n minus 1 disk from A to B using C. 그죠? That's the basic step. Because in order to move the bottom one, I don't have to have anything in C. 그죠? 이게 일로 가려면 여기 비어 있어야 되잖아. 이제 결국에는 이게 있는 게 여기로 다 가 있어야 되죠. 그죠? 그 얘기하는 거예요. 그 얘기하는 거. 번역하고 있네. Move top n-1 disk from A to B using C. That's the main idea of doing it. 아이고. Move everything in B. But this is very abstract view. I mean, in order to move everything into B, I had to go through a lot of moves, right? They didn't just show you. I just simply say, this is the bottom stage that I have to do before I move 1 to C. So that is another problem. It is another Towers of Hanoi problem, moving n-1 disk from A to B, not A to C. What is 2 problem again here? Moving the bottom disk to C, moving the n-1 disk to B. That's 2 separate problems now. So I can apply recursion there. Move the top disk from A to C. Because I can do this, now B has all the stuff. Moving top n-1 disk from B to C using A. B to C using A. So, B to C using A. So that's another move I have to make. Ta-da. Moves when n disk is 0, n is 0. Moves n disk 2 times move n-1. A to B, B to C. n-1 disk. 그죠? No? Yes? Yes? No? We just got the idea of, right? n-1 disk A to B first. After I move the bottom disk to C, now I have to move that n-1 disk in B to C. That's why moving n-1 times 2. This is how much moves that I need to take for moving n-1 disk. But I have to do it twice in order to everything to go to C. Plus 1, moving the last disk into C. 됐지? Okay? No? Yes? No? Okay. 그냥 뭐 to the n이고 뭐고 신경 쓰지 말고 이렇게 생각하면 돼. In Korean briefly. 지금 볼 때 처음 시작할 때 이렇게 됐죠. 아주 가장 쉬운 솔루션을 주자면 리커시브 나는 처음에 어떻게 배웠냐면 그냥 외웠어. 도저히 이해가 안 가갖고 외웠어. 근데 이렇게 설명을 해주니까 조금 이해는 갔었어. 부셔가지고 계속 부셔서 하나 옮기고 2개 옮기고 똑같은 얘기 여기서 하는 거야. 지금 봐봐. 여기에서 문제가 이렇게 있단 말이야. 이거 삼각형으로 해서 그렇지 이거 하나하나 다 디스크 이렇게 쌓여 있는 거야. 그죠? 그래서 뭘 해야 돼? 제일 먼저 해야 될 게 뭐예요? 뭐 알고리즘이고 뭐고 떠나서 그림만 딱 보고 해야 될 게 뭐야? 문제 자체는 모든 A에 있는 거 C로 가는 거지. 그죠? 근데 A에 있는 거 C로 가려면 제일 먼저 해야 되는 게 제일 큰 게 아래로 가 있어야 나머지를 옮길 수 있을 거 아니야. 그러니까 나는 그게 제일 첫 문제야. 얘를 일로 가는 거. 그러기 위해서는 이 위에 있는 것들이 C에 있으면 안 되고 전부 다 B로 가 있어야 되겠지. 그죠? 그래야 내가 얘를 여기로 옮길 수 있으니까. 그러니까 내가 n-1 디스크를 일로 옮기는 게 얼마 걸리는지를 보는 거야. moves n-1. 그렇죠? 옮겼어. 쫙 옮겼어. 오케이. That's 여기 있는 표현으로 따지면 몰라. 몇 번이 걸렸는지 몰라. move. That's how many times it takes from A to B. Okay. What else? Then after this 뭐 해야 돼? 저기 A에 있는 거 이런 거 일로 옮기면 되죠? 그죠? Done. 그죠? 그럼 뭐 해야 돼? What's the last step of doing it? I'm simplifying most of the stuff. 이거 여기로 옮겨야 되지. 그죠? That's another move. Move n-1. 그죠? Hopefully everything will be in C. I know. In order to move everything in B to C, you also go through a lot of complicated steps. But that's a single problem with solving Hanoi. I mean, we all know how to do that for a single disk, 2 disk, 3 disk. 그러니까 it's not a problem. That's why they say 2 moves. 이거. 여기서 이렇게 써놨죠? And plus 1. That's how much time it takes to move n disk. 이렇게 써놓은 거예요. If you do this, it will give you a 2 to the n-1 minus 2 to the n minus 1 moves. This better more detailed explanation on section 2, chapter 2, when they explaining the recursive. I forgot the number, but if you take a look at this explanation on your textbook, they're referring to section 2.53. 내 정확한 번호 잊어버렸어. Do take a look. So that's how we look at for recursive way of solving this towers of Hanoi problems. Many other examples for recursive, but we're not focusing recursive at this time. We're focusing on the stack examples. Okay. So that's good. 3 disk, okay. 33. What about 64 disk towers of Hanoi disk problems? Can you do this? We can compute how many moves that we need, right? 2 to the 64. 2 to the 64면 도대체 얼마야? 2 to the 64. 64비트네. 64비트. 64비트의 모든 컨비네이션이네. 우리 요즘에 나오는 CPU가 몇 비트지? 이번에 iOS 아이폰 5가 몇 비트지? 뭐 64비트라고 안 그래? 64비트 CPU 뭐 이렇게 얘기 안 해? 아직 우리나라에 아직 안 나왔지. 그게 먼저 팔고 있죠, 그죠? 맞아, 64비트 맞을 거야. Move 64 disk. That's how much it takes. That's 1.8 times 10 to the 19 approximations. That's a lot of number. A lot of moves that I have to make in order to move 64 disk from A to C. 64. How long does it take to move 64 disk by the priest? That's a classical problem. That's the 무슨 스님 priest가 뭐야? 수도승들이 저거 옮기는 게 그 Towers of Hanoi problem 책에 보면 나와요. But for us, by us, how many times it takes? Assuming at 1 disk per minute, 1 disk per moves per minute, then these people would take about 3 times, 4 times, 10 to the 13 years. I don't even know how many years that takes. 이거 얼마야? 몇 조년인가? 모르겠다. I don't know. According to the legend, the world will come to an end when the priests have complete their task, which means it's impossible in the living times. How long would it take to move 64 disks by Pentium 5? I'm sorry, I don't have any other better machines. Pentium 5. Performing 10 to the 9 moves per second. 10 to the 9 moves per second. A Pentium 5 would take about 570 years to complete 64 disk move. Simply say we program this 64 disk move in your computer. Pentium 5. Pentium 5라고 안 쓰지. 요즘 뭐야? What's the name of the CPU nowadays? I forgot to keep track of it. 뭐야? 요즘에 CPU 뭐야? 요즘 많이 쓰는 거 뭐예요? i5, i3. Well, Pentium 5 is maybe close to i3, maybe next version of i3. Previous version of i3. Let's change the name. So it takes 10 to the 9 moves per second. This computer can do a 10 to the 9 moves per second, but still takes 570 years to move every disk into the C. It takes a long time. To simply show you the recursive would take a lot of computation time. 3 disk to 64 disk, a lot. 그죠? Things to look at here. It is not about how much time it takes. It's about that we can use a stack to solve this problem. It's one of the applications of stack. Okay? Do not focus too much time on how much it takes. That's not the problem. Stack using stack and bit of techniques for recursions. We can solve this. We can provide the algorithm to solve this Towers of Hanoi problems. That's the bottom line. This is just for your fun. 또 외우고 그러지 마. 뭐 570명 걸리고 뭐 이런 거 외우고 그럴 필요 없어요. Okay, that's almost it for stack, but it will come up again when we're discussing the next data structures. Just simply to show you the comparison between 2 data structures, 2 different algorithms for it. Rearranging railroad. This is another application of using stack. Of course, there are many others. in your textbook, if you take a look at 289, I think it's 289. 맞는지 한번 확인해 줄래? Can you look at page 289, those of you who have a text? 날라리 학생들 책도 안 가져가지고. 289. Can you check and can you see the Is it there? Do I have a right page number? 있지? Okay. So please read problems in 289. It will come again for next chapter as well. But I think I would just briefly introduce the problem of doing this. If you read 289, which most of you probably don't read it at all, but you will have to because it's on your assignment 3, if I remember correctly. Read. It's a problem of rearranging a railroad cars, rearranging the cars at the shunting yard. It's like a station, and has an input track and output track, and K holding tracks between input and output tracks. So I have something in the middle. I have to rearrange. I have to, for example, I have to sort the train numbers the correct way. So what part can I use a stack to represent this problem? If you take a look at it, 나 자꾸 까먹어. It's a railway. It's an input track. I'm just doing this because some of you probably not read your textbook. This is output track. Output track, they call it. What does the train look like? 어떻게 생겼어? Trains look like what? It's like a linked list. 그죠? Trains look like. And this one is like a cargo. They have numbers in it. Maybe this is cargo number 3, 2, 9, 4, 7. I don't know. If this travels around, they need to take one by one. Go to the next station, maybe I need to drop 7. Next station, I need to drop 4. So I'm doing a delivery. 그죠? But if this number is mixed up, then I got to some station, but they need some cargo right in the middle. Then what do you have to do? You have to disconnect all of it, put it out. That takes time. So efficient way is probably I just sort them out as in the delivery order. So for example, maybe if this is a problem, then I'd like to have a 2, 3, 4, 7, 9. So I can go and drop it 9, 7, 4, 3, 2 this way. I don't know which way it is. But this is where it begins, the train begins. And they like to sort this. But railway is usually very expensive, 그렇죠? 이거 하는데 어떻게 해? How do you reorganize this? It'd be nice you can just use some pickups and do this, but that's not the case. 이렇게 들었다 하고 하면 훨씬 편할 텐데 그렇게 못하죠. So in order to solve this, they built another track like this. Side tracks. Side tracks. You got the idea now. This is stack 1, stack 2, stack 3. Okay. So when train is here, maybe I would do this 3, 2, 9, 7, 4. Well, so and I can find out which one to pop it first. Obviously, I want to pop the 2 first. 그죠? So how can I use these 3 stacks to, at the end, I like to have 2, 3, 4, 7, 9. Go. This is the rearranging railroad problems. What kind of algorithm do you need to put the numbers in here? Using stack. Okay? Of course, in your textbook, give you a very nice example on how to do this. I wasn't supposed to explain you this, but I just give you the problem, and then you can think of it yourself for your assignment 3 solutions. Okay? 이거 어떻게 하면 되는지 책에 답도 다 나와 있어. 근데 다는 안 나와 있어. 중간에 설명하다 말아놨어. 이렇게 뻔하니까. 읽어봐요. I will go back to this. I will come back to this for the next chapter. We'll be discussing this again. So those of you who are not reading the textbook, this is a problem that you try to solve for. And you can certainly use a stack. There are a few issues in this problem. How many stacks do you need? Or what order should you put these boxes in? See figure 8.6 for 3-track examples. If you take a look at 8.6, you see these 3 lines, 3 stacks. But they don't draw this. It's a bit difficult to understand the first timers. Okay. And 8.7 give you which order you should take these numbers in, which sequence, so you can have a sorted number out there. Okay. So 8.7 is your solution. 8.9, 8.10 is a program to show you how to actually implement those stuff. So basically, 8.7 gives you the algorithm and translation to the C++ code. Again, I will come back to this for the next chapter as well. 좋지? So we all have rearranging railroad problems now. 책을 요거는 꼭 읽어봐야 될 거야. 알겠죠? Okay, that's it for stack. Any questions for the stack? Another data structure, but it's almost similar to the linear list. Stack was almost similar to the linear list, but has some restrictions in it, right? Same thing. It's another version of linear list with different set of restrictions than stack. But usually, you guys know this already. Stack is last in, first out. This one, first in, first out. Like the lining up for your bus stations. Like a stack, it's a special kind of linear list. I just have a set of elements in it, done. One end is called front, the other end is called rear. Front and rear, top and bottom. Same word, but they like to use a different vocabularies for this. Addition. It's a linear list. I mean, basic operations that I have to do is adding an element, remove an element, find out whether this list is empty, find out how many elements in my list. 그죠? That's the basic operations to do it. Addition is sometimes called an insertion. Insertion is the term that we use in array list. NQ is most likely the ones that we'll be using for the queue example, NQ. We don't use the word here for push. Push might be confusing. Push is just for the stack. Are done for rear end only. I only add elements at the back, not into the front. If you start adding an element to the front is a what? Stack. Like removals, deletion or DQ. Taking one out of the queue is something called DQ. NQ and DQ. NQ는 queue에 집어넣는 거. DQ is taking one out of the queue. are made from front only. You only take out the elements in the front. You add an element at the back and you take on the front. That's why you can call it as first in, first out. First in, first out. We know this. First in, first out. Let's take this as a front. Front, rear, element in here, out of the queue here. It's a queue. It's a queue. Later. I don't know how many of you will be taking such course. There is something called queuing theory. Queuing theory. When you actually analyzing the performance of something, everything that you can design for is actually queue. Your computer is actually queue. CPU is also queue. The concept-wise, I mean, if you want to find out how fast your CPU is, you can use these queues to analyze how fast your CPU is. I mean, you can do a modeling on top of it. Queuing theory is a very deadly course. 정말 듣고 싶지 않은 과목 중에 하나일 거예요. 다 나오니까. 나중에 아마 학부에서는 거의 들을 일 없고 뭐 나중에 대학원을 가거나 유학을 가거나 하면 듣게 될 수 있는 몇몇 친구들이 있을 거예요. 그러면은 듣지 말고 그냥 때려치고 나와요. 꼭 들어야 되는 거 아니면. 이렇게 그리면 이게 나중에 되게 심오해져요. 짜증나요. 짜증나요. So that's a queue. We call this as a queue. Also, queue is well used for internet environment too. Queue when you use your routers, and when we discuss stuff like in Introduction to Computer Science, we discuss like networking, internet, those devices on the web, those stuff, everything is queue. In your computer, your programs and operating systems, your programs that you use, everything is using a queue inside. So, the very dumb example, I don't know why I have this here. Bus stop, front, rear. Because not my animation, I don't choose to do this. So when you have a one person in a queue, front, rear, same. Because I don't have anything. Another one comes in, rear, change to the next one. Another one comes in, rear is now the sky. Again, I didn't do this. 내가 한 거 아니야. 누가 해준 거 내가 좀 갖다 쓰긴 했는데 별로 이렇게 내가 이렇게 그 미술적 감각이 떨어지진 않아요. 그냥 이해해요. Rear. So when the bus comes, remove a person from a queue from the front. Front moved. Notice that the front now is moved to the next one. So you can think of it as a pointer. Front pointer is now to the next one. It's like going through the linear list, linked list. Doesn't matter, array or linked list. Front, rear, add a person to the queue. Always you adding to the back. Queue is FIFO, first in, first out list. Very stupid examples. So often, if I giving you a programming assignment for this queue, then I usually do this. Typical programming assignment like using queue is probably give you the idea for program a cashier. When you go to 이마트나 홈플러스 가면 what do you see? When you try to pay your stuff, what do you see? 코스코 가본 사람. 양재동에 있는 코스코. 부모님들은 가실 텐데 전혀 관심들 안 따라다니니까 저는 모르죠. 코스코 가보면 줄 엄청 길지. 에이, 코스코 모르니까 이마트 하자. 이마트. When you go to Emart, when you try to buy your stuff, you will see a cashier. person sitting here, person sitting here, person sitting here. 그죠? When you go to the at night times when there are a lot of people try to buy stuff, they usually turn on many cashier on it, and people line up with their card in this way, one by one. 그죠? What is the smart way of moving out this cashier fast? What do you do? What do you actually do? You actually try to look at the queue, less number of people in the queue. You just try to find it. I'm standing here, I see a lot of people waiting, I see no people waiting, I go there. 그죠? That's the typical way of doing it. Typical programming assignment like is, I put this as a queue. People comes in. And this person would take about 2 seconds per customer. This cashier is slow, 2 seconds. This cashier is slow, takes 5 seconds. This cashier is very experienced one, so 0.5 seconds. This one doesn't know what to do, intern, 10 seconds. And I say there are 10 customers. I have 4 counter, cashier, open. How long does it take to finish 10 customers to move out of the queue? Everyone. Which one is the best way of doing it? Typical queuing example problems. And you do this multiple times. You do this 10 customers, 20 customers, 30 customers, 40 customers. And you also do this with 3 cashier open, 2 cashier open, 1 cashier open. And after do this many different combination of values, maybe you can find the optimum number of cashier to open at all times or from time to time. 이렇게 계속 해가지고 저녁 7시부터 9시까지에는 캐시어를 3명은 놔야 평균적으로 뭐 10초 안에 다 나가더라, 5초 안에 나가더라. 그거 그냥 사람 많으면 그냥 캐시어 열고 막 이러는 거 같죠? 이거 프로그램 짜갖고 시뮬레이션 하는 거야. 하루에 사람 들어오는 시간 7시부터 사이에는 한 1000명이 쇼핑하러 들어오더라. 1000명이면 몇 개를 열어야 그 모든 커스터머가 10초 안에 계산하고 나갈 수 있느냐, 그런 거. 근데 사람이 1000명에서 갑자기 1500명이 되면 10초 안에 다 못 나가니까 하나 더 열어야 된다, 안 된다. 그런 거 시뮬레이션 할 수 있는 프로그램. Good, very easy simulation type of programs for your queuing assignment. Of course, if I'm giving you, I'm gonna make it very easy. Every cashier is probably the same. 1 second, 1 second, 1 second. But I'm gonna make a difference in somewhere around here. Or I can make this as exponential distribution. Everyone will be different every single time. So it's a supermarket simulation programs. You can now you learn a bit of Q. You can write your own simulation programs like this. So simulation is nothing fancy. It's the same thing. If you know one data structure, then you can start building one yourself. Maybe I can give you this as assignment 5 later. I don't know. I haven't decided yet. I wasn't planning to give you the program assignment during the course, maybe towards the end of the course. But I'm just saying this is typical assignment questions like. 한번 할 수 있겠지? 이거 뭐 어렵지 않겠지? 이거 뭐 해봐야 더하기 빼기밖에 없어요. 나오는 사람 몇 초 걸리는지 더하고 평균 구하고 더하고 평균 구하고 Q 3개 했을 때 4개 했을 때 해갖고 평균적으로 한 명당 얼마 걸리는지 계산해서 그냥 더하기 해서 나누기만 하면 되는데 별거 없어요. 사실 Q를 몰라도 할 수 있는 거야. 그죠? Q를 하면 좀 더 쉽게 구현할 수 있는 거예요. 나도 이런 거 했던 것 같아. 잘 기억을 안 나는데 하도 오래돼서 기억은 안 나는데 그랬던 것 같아요. 이건 스택하면 안 되겠지? 이걸 스택으로 바꾸면 어떻게 돼? 난리 나겠죠. 제일 끝에 오는 놈부터 먼저 계산해 주니까. 그렇게 되면 어떻게 돼? 맨 앞에 있는 놈들은 계속 기다리기만 하고 계산을 못 받을 수도 있죠. 그죠? So some questions in this chapter will ask you whether some problems can be programmed with the queue and asking you whether they can be replaced with a stack. Replaced with the stack. And asking you whether that's possible or not. This one seems to be a bit difficult to replace with the stack. 그치? 이거는 좀 스택으로 하기가 좀 곤란해 보이기도 한다. 그죠? 모르겠다. 될 수도 있겠지. 다른 방법을 찾아보면. 지금 봐서는 좀 힘들 것 같아요. Okay, so this is back to this slide. QADTs, abstract data type queues. Now it's about to memorize everything. 이건 너무 많이 봤어. We've seen this too many times. Too many times. But we all know there are slight differences, variations of each ADTs. This one is ordered the linear list. One end is front, the other end is rear. Operation empty, return true. If the queue is empty, return false. Otherwise, by looking at that, if I'm using an array implementation, array list that we looked at in stack, maybe this one we can just simply use the empty function from arrays, or not arrays, array list class that we looked at in stack. So it's probably the same. Size, return the number of elements in the queue. Likewise, we can just rely on array list size functions in it. Front, return the front element to the queue. If you look at the bottom here, there are two, array list representation, linked list representation. And front is the one that says return the front element of the queue. 그게 뭐야? What is the front? How do you look at the first element in the list array? 뭐야? 0, position at 0. That's the first element. Front. Back. Return the back or rear element of the queue. If I put the front as a 0, rear is at the back, but I have to find out how many elements in the list first. That element's location is probably the last one in the queue. So pop, I'm sorry, I should, in your textbook it says pop, but it should be replaced with the DQ and Q, but I just leave it there. Pop, DQ, push, NQ. So DQ and NQ. It is also possible to represent the queue using array-based representation, linked list representation, just like stack and just like linear lister that we have looked at so far. So I guess we can take a look at that for next class. Okay, I think I'm gonna stop here today. About the assignment, can you, 나갈 때, you can give your assignment to these two people, nice people. 나 때문에 이거 해주잖아, 맞아? I'm gonna call out the attendance now.